two-dimensional harmonic oscillator. That is, a 2D harmonic oscillator is like this one. So this one is a linear harmonic oscillator, one-dimensional linear harmonic oscillator. Okay, so one more spring I am attaching to this one. Okay, so it can oscillate now in two directions. One is x direction and in y direction also. So there is two directions of oscillation. Okay, so this spring constant is ky and this is calling us kx. And what is this kx? Kx is m omega x square. Omega is the angular frequency in the x direction and this is equal to m omega y square. Omega y is the angular frequency in the y direction. Okay, that is, we can find out the potential. V of xy is equal to, there are two potential, right? That is half k x square plus half k y square. That is, V of xy is equal to half. We know kx is equal to m omega x square plus half m omega y square. And we can find out the energy. That is, for one-dimensional case, we now E is equal to nx plus half h cross omega x. Here there is one more term, therefore ny plus half h cross omega y. And wave function psi is equal to psi of x into psi of y. That is, psi is equal to, we know psi x, what is that? That is alpha by 2 raised to n factorial root pi all raised to half e raised to minus half alpha x square into hn of alpha x. And similarly we can write psi of y, that is alpha by, that is alpha y, here it is alpha x, okay, by 2 raised to n factorial root pi all raised to half e raised to minus half alpha y square hn of alpha y. Now I am going to consider an isotropic 2D harmonic oscillator. What is the peculiarity of this isotropic 2D harmonic oscillator? That is, isotropic means the angular frequency in the x direction and the y direction will be same. That is, omega x is equal to omega y is equal to omega. So we can write the energy expression E is equal to nx plus half h cross, see, omega x equal to omega, that is omega plus ny plus half h cross omega. That is, we got energy is equal to nx plus ny plus 1 into h cross omega. This will be the energy of a isotropic 2D harmonic oscillator. Similarly, we get the wave function also. That is alpha by 2 raised to n factorial root pi into e raised to minus half alpha square into x square plus y square into hn of alpha x hn of alpha y. Okay, this will be the expression for energy and wave function of isotropic 2D harmonic oscillator. Now let us discuss 2D LHO degeneracy. That is, I already told you what is this degeneracy. That is, if two states have same energy eigenvalue, then the degeneracy is 2. Okay. So here we are considering an isotropic 2D LHO. That is just before we find out the energy. That is, energy expression will be equal to nx plus ny plus 1 h cross omega. And here this nx can have values 0, 1, 2, etc. and ny can have values 0, 1, 2, etc. Earlier when we are discussing about degeneracy problem, we made a table. What is that? That is nx plus ny, nx comma ny, nx plus ny plus 1, and it's increasing order. Then the energy expression, that is nx plus ny plus 1 into h cross omega, then the wave function, then the degeneracy. So first I am going to take nx equal to 0 and ny equal to 0. So nx plus ny is equal to 0 and nx 0, ny 0. And nx plus ny plus 1 is 1. Next, I am taking nx equal to 0 and ny equal to 1. That is 1. Here nx equal to 0, ny is 1. There is other combination is also possible. That is 1, 0. Okay. So for this combination also nx plus ny is equal to 1. Okay. And here it is 2. For both the case it is 2. Now 2. Okay, next energy state is 2. That is, I can take nx as 0, ny as 2, or nx as 2, ny as 0, or nx is 1, ny is 1. Okay, so here we get this is equal to 3, here also 3, here also 3. Now third one, that is, I can take nx equal to 0 and ny 3, or 3, 0, or 1, 2, or 2, 1. Okay, so for all those cases, I will get 4, 4, 4. Right, that is increasing order is 1, 2, 3, 4. That is energy is h cross omega, 2 h cross omega, 3 h cross omega, 4 h cross omega. That is, this one is ground state, right? Both nx and ny are 0, therefore it is ground state. Then this is first excited state, this one is second excited state, and this is third excited state. And what is the corresponding wave function? That is psi nx ny. This is nx equal to 0, ny is also 0. And other one is nx is 0, ny 1, and there is one more wave function, that is 0, 1. And here there are three wave functions, that is psi of 0, 2, psi of 2, 0, and psi of 1, 1. Here there we can have four wave functions, that is 0, 3, psi 3, 0, psi 1, 2, and psi 2, 1. That is, here degeneracy is 1. Here two states, psi 0, 1 and psi 1, 0 have same energy. Therefore, degeneracy is 2. Here psi 0, 2, psi 2, 0, psi 1, 1 have same energy. Therefore, degeneracy is 3. And here it is 4. So, let us make a conclusion. What is the conclusion? Degeneracy of nth excited state of a 2D isotropic oscillator is equal to n plus 1. Example problem. Let us consider a 2D linear harmonic oscillator. And for this 2D linear harmonic oscillator, the omega x is equal to omega and the omega y is equal to 2 omega. That means this is not an isotropic oscillator because frequency of oscillation is different in different directions. And we know the expression for energy of a 2D harmonic oscillator, that is E is equal to nx plus half h cross omega x plus ny plus half h cross omega y. So we can substitute these values, omega for omega x and the 2 omega for omega y. That is, we will get E is equal to nx plus half h cross omega plus ny plus half h cross 2 omega. That is equal to nx plus half h cross omega plus 2 ny plus 1 into h cross omega. That is, we got energy expression E is equal to nx plus 2 ny plus 3 by 2 h cross omega. And here this nx can have values 0, 1, 2, etc. And ny also can have values 0, 1, 2, etc. So let us make a table, that is nx plus ny, nx comma ny, nx plus 2 ny plus 3 by 2, and their increasing order. Then energy is equal to, we know, nx plus 2 ny plus 3 by 2 h cross omega. Then the wave functions, then degeneracy. Okay, so first combination. First I'm taking nx equal to 0, ny equal to 0. That is 0. Okay, so the combination is 0, 0, and this will be 3 by 2. Next combination is nx plus ny is equal to 1. So first I'm taking nx1, ny 0. Okay, so nx is 1, ny is 0, that is 1 plus 3 by 2, 5 by 2. Next I'm taking 0, 1. Okay, for 0, 1, nx is 0, ny is 1, therefore 2 plus 3 by 2, that is 7 by 2. Okay, then next higher state is 2, nx plus ny equal to 2. That is, I can take nx is equal to 1, ny is equal to 1, and I can take nx2, ny 0, and 0, 2. So if you are taking 1, 1, then nx is 1, ny is 1, therefore 1 plus 2, that is 3 plus 3 by 2, that is 9 by 2. And the 2, 0, nx is 2, 2 plus 3 by 2, that is 7 by 2. And other is 0, 2, that is 2 into 2, 4 plus 3 by 2, 11 by 2. Okay, similarly you have to find out 3, that is the different combinations are 0, 3, 3, 0, and 1, 2, 2, 1. Okay, and find out the corresponding nx plus 2 ny plus 3 by 2 value. Okay, and then rearrange in the increasing order. That is, this is 3 by 2, then 5 by 2, then 7 by 2, then 9 by 2, then 11 by 2. Okay. So for 3 by 2, the energy is 3 by 2 h cross omega, 5 by 2 h cross omega, 7 by 2 h cross omega, and 9 by 2 h cross omega, and 11 by 2 h cross omega. So this is the ground state. This is energy of first excited state. This is energy of second excited state. This is energy of third excited state, and so on. Okay. So the wave function 3 by 2 is corresponds to only one state, that is psi 0 0. Therefore the degeneracy is 1. Now 5 by 2. 5 by 2 also only one state have 5 by 2, that is psi 1 0. So degeneracy is 1. 7 by 2, see 7 by 2 and one more 7 by 2 is there. Okay, so this is corresponds to this state and this is corresponds to this state. That is, if psi is 0 1 and if wave function is psi 2 0, both have same energy, that is 7 by 2 h cross omega. Okay, so the degeneracy is 2. And similarly, if you find the values for these terms, you get more terms here, and you can find out the further energy state. Maybe some other state will have this 9 by 2 h cross omega. So I can write the degeneracy right now. Okay, so this is a work for you. Find out the wave functions corresponds to 9 by 2 h cross omega and find its degeneracy. Now let us consider 3D isotropic linear harmonic oscillator degeneracy. That is, all the angular frequencies are same. Omega x equal to omega y, and that is equal to omega z is equal to omega. So it is oscillating in all the direction with the same angular frequency. And we know the expression for energy, that is E is equal to nx plus half h cross omega x plus ny plus half h cross omega y plus n z plus half h cross omega z. This is the general expression for energy. But here all the omega x, omega y and omega z are equal. Okay, therefore this expression reduces to E is equal to nx plus ny plus nz plus half into h cross omega. This is the expression for energy of a 3D isotropic linear harmonic oscillator. Now we have to find out the degeneracy. And here you can see the nx can have values 0, 1, 2, 3, etc. And ny can have values 0, 1, 2, 3, etc. And nz also can have values 0, 1, 2, 3, etc. Okay, so you have to make a table, that is nx plus ny plus nz, nx comma ny comma nz, and nx plus ny plus nz plus 3 by 2, and it's increasing order. Then energy E, that is nx plus ny plus nz plus 3 by 2 h cross omega, then the corresponding wave function and the degeneracy. Okay, so first I am taking nx is 0, ny 0, nz 0, that is this is equal to 0, and these are 0, 0, 0, and this will be 3 by 2, and next one nx plus ny plus nz equal to 1. So I can take nx 1, ny and nz 0, and I can take nx 0, ny 1, nz 0, and 0, 0, 1. So here I will get 1 plus 3 by 2, that is 5 by 2. Then 2. 2 I can make 1, 1, 0 or 1, 0, 1 or 0, 1, 1. And other combinations are 2, 0, 0, 0, 2, 0, 0, 0, 2. Okay, so I will get 2 plus 3 by 2, that is 7 by 2. And if you are taking 3, you can make 3 by combination 1, 1, 1 or 1, 0, 2 or 2, 0, 1 and many other combinations also you can make. Please try it by yourself. So for all this state, you will get energy 9 by 2. Okay. So this increasing order is 3 by 2, 5 by 2, 7 by 2 and 9 by 2. That is the corresponding energies are 3 by 2 h cross omega, 5 by 2 h cross omega, 7 by 2 h cross omega and 9 by 2 h cross omega. And the corresponding wave functions are, here it is psi 0, 0, 0 and for 1 the corresponding wave functions are psi 1, 0, 0, psi 0, 1, 0, psi 0, 0, 1. Okay, so only one state have this energy, therefore its degeneracy is 1. And here 3 states have same energy 5 by 2 h cross omega, therefore degeneracy is 3. And here there are psi 110, psi 101, psi 011 and psi 200, psi 020 and psi 002. 6 states having the same energy 7 by 2 h cross omega, therefore degeneracy is 6. And here you will get total 10 states, 10 combination of nx, ny and nz. So you will get 10 states here. So the 10 states have same energy 9 by 2 h cross omega. So the degeneracy of all the states, that is psi 111, psi 102, etc. have a degeneracy 10. So we can make a conclusion or general expression, that is, if n is equal to nx plus ny plus nz, then the degeneracy of 3D isotropic harmonic oscillator will be equal to n plus 1 into n plus 2 by 2. That is, if n equal to 1, see, n equal to 1, then what will be the value? 1 plus 1, that is 2, and this 2 and the 2 will cancels, and remaining is 1 plus 2, that is 3. That is we got here, right? And if n equal to 2, then degeneracy will be is equal to n plus 1, that is 2 plus 1 into 2 plus 2 by 2. Okay, so we can cancel 1 of 2, so you will get 6, right? Okay, so this is the general expression to find out degeneracy of a 3D isotropic harmonic oscillator. Okay. Asymmetric linear harmonic oscillator. So before discussing about asymmetric linear harmonic oscillator, we need to discuss about symmetric linear harmonic oscillator. So first I am going to discuss about symmetric linear harmonic oscillator that we already discussed, right? What is this potential of a linear harmonic oscillator? That is V is equal to half k x square, and this value is same for both the region, that is x is greater than 0 or x is less than 0. That is, the potential function look like this one. This is x and this is v of x. In the both the region, that is in the negative x region and in the positive x region, this have a same potential, that is v is equal to half kx square. And we got the corresponding wave function, that is psi n of x is equal to root of alpha by 2 raised to n factorial root pi e raised to minus half alpha square x square h n of alpha x, where I told you h n is Hermite polynomial. And this n can have values 0, 1, 2, etc. So the corresponding different Hermite polynomials are h0 of alpha x is equal to 1, h1 of alpha x is equal to 2 alpha x, and h2 of alpha x is equal to 4 into alpha x all square minus 2, and h3 of alpha x is equal to 8 into alpha x all cube minus 12 alpha x. And here at x equal to 0, okay, at x equal to 0, various Hermite polynomial, that is h1, that is you see there is a x. Okay, so when x equal to 0, the Hermite polynomial h1 will be equal to 0 and h3 also will be equal to 0. See, x is there. Okay, and h5 also will be equal to 0. Okay, so these terms will be equal to 0. That is odd terms. So corresponding the wave functions. Okay, so corresponding wave functions, that is psi 1 equal to psi 3 is equal to psi 5 etc. will be equal to 0. That is odd wave function will be equal to 0 at x equal to 0. Okay, for a symmetric linear harmonic oscillator. Now let us discuss the asymmetric linear harmonic oscillator. For asymmetric linear harmonic oscillator, the potential V of x is equal to half k x square for x greater than 0 and infinity for x less than 0. That is, if we plot this potential function, we get, okay, see here the potential is infinity. That is, this is the forbidden region for the particle. So the particle can oscillate only in between this region. Here it can oscillate between this entire region in the negative axis and the positive x-axis. But here the particle can oscillate only in the positive x region only. Okay, this region only, right? And this potential is half k x square. So similar to this one, at x equal to 0, the potential V of x is equal to infinity. That means at x equal to 0, the wave function psi of x must be equal to 0. That is the boundary condition, right? That is, the negative x region is forbidden to the particle. There the potential is infinity. Okay, so there will not be any chance of finding the particle. So at x equal to 0 and less than x equal to 0, the wave function should be equal to 0. Okay, that is why we got this condition. That is, this wave function psi of x must be vanished at x equal to 0. And this condition is satisfied by the Hermite polynomial h1, h3 and h5. So the corresponding wave functions are psi 1, psi 3 and psi 5. and etc. That is odd one, right? Therefore, for the asymmetric LHO, the wave function psi n of x is equal to root of alpha by 2 raised to n factorial root pi e raised to minus half alpha square x square hn of alpha x, and energy En of x is equal to n plus half h cross omega, but here the n value should be 1, 3, 5, 7, etc. So the ground state is corresponds to n value 1, first exit state is corresponds to n value 3, and second exit state is corresponds to n value 5, and so on. Okay, so this is the equation for wave function and the energy of a 1D asymmetric linear harmonic oscillator. And please remember these things. That is, ground state is corresponds to n equal to 1, and the first exit state is corresponds to n equal to 3, and so on. Only odd values of n is possible. This is the wave function and the expression for energy of a 1D asymmetric linear harmonic oscillator. Okay, so this is the graphical representation. So there is a potential V of x that is equal to half k x square in the region where x greater than 0, and that is equal to infinity when x is less than 0. That is, it is look like this one. Okay, so this region is forbidden region for the particle. Here the potential is infinite, and the particle have a finite energy, so it cannot overcome this infinite potential barrier. Okay, so the particle is trapped in this region. Okay, or it can oscillate in this region only. So the ground state, the first state, possible state is psi 1, and the corresponding energy is E1, that is equal to 3 by 2 h cross omega. The next state is psi 3. Okay, and the corresponding energy E3 is equal to n is 3, that is 7 by 2 h cross omega. And next possible state is psi 5, that is E5, that is equal to 11 by 2 h cross omega, and the next state is psi 7, and E5 is equal to 15 by 2 h cross omega, and so on. So this is the ground state. Okay, this is the first excited state, this is second excited state, and this is third excited state, and so on. So sometimes they will represent in a question or something, they will represent this as ground state psi 1, okay, and this is psi 2, and this is psi 3, and this is psi 4. Okay, so if it is specified for 1D asymmetric LHO, then it means the states are psi 1, psi 3, and psi 5, and psi 7. Okay. Example problem. Here, a linear harmonic oscillator potential is given, and from the given potential, we can understand that this is a asymmetric harmonic oscillator, right? Because in the negative x region, potential is infinite. Okay, so this is a asymmetric linear harmonic oscillator. In the question, it is not specified, but from the given potential, we can identify this as a asymmetric linear harmonic oscillator. Okay, and it is 1D oscillator because only x. Okay, therefore it's a 1D asymmetric linear harmonic oscillator, and the wave function is given. And the question is to find out the average energy, that is expectation value of E. Earlier, I told you the expression, that is expectation value of energy is equal to summation over S, ES, PS, where PS is the probability of each state and ES is energy of each state. So here what are the states? States are psi 0, psi 1 and psi 2. That is psi is equal to 1 by root 2 psi 0 plus 1 by 2 psi 1 plus 1 by 2 psi 2. So these are the coefficient, right? And this is already a normalized wave function. So the square of the coefficient will be P1. That is, we will get P1 is equal to 1 by 2 and P0 equal to 1 by 2 and P1 is equal to 1 by 4 and P2 is equal to 1 by 4. That is square of the state, right? 1 by 4. So we got the probability of each state. Now we have to find out the energy. Energy of psi 0 wave function, energy of psi 1 wave function and energy of psi 2 wave function. That is, we know this expression for asymmetric LHO, 1D LHO, energy En is equal to n plus half h cross omega, and where n is equal to 1, 3, 5, 7, etc. only. Okay, there is no n equal to 0, no n equal to 2 and even values. Only odd values are possible for n. So this I0 is corresponds to ground state. This one is corresponds to first excited state and this one is corresponds to second excited state. So the corresponding n values are, this one is ground state n value, this one is first excited state n value, this one is second excited state n value. Okay, so we will get E0, that is ground state energy, that is equal to, we have to substitute n equal to 1, right? That is 3 by 2 h cross omega. Second one is E1, that is energy corresponds to psi 1, that is equal to, that is first excited state, right? That is n value is 3, that is 3 plus half, that is 7 by 2 h cross omega. And next state is psi 2, corresponding energy is E2, and for E2 n value is 5. Okay, so when substituting 5 you get 11 by 2 h cross omega. Now we can substitute all this value in this expression. That is, expectation value of E is equal to E0 P0 plus E1 P1 plus E2 P2. Now let us substitute all these values. That is, E0 is 3 by 2 h cross omega into P0 is 1 by 2 plus E1 is 7 by 2 h cross omega and P1 is 1 by 4 plus E2 is 11 by 2 h cross omega into 1 by 4. That is equal to 3 by 4 h cross omega plus 7 by 8 h cross omega plus 11 by 8 h cross omega, that is equal to, we can multiply this by 2 and divide by 2, that is 6 by 8 h cross omega plus 7 by 8 h cross omega plus 11 by 8 h cross omega, that is equal to 24 by 8 h cross omega, that is 3 h cross omega. Another example problem. Wave function size given, that is equal to 2 by root 3 psi 0 plus I by root 3 psi 1. The question is to find out average energy E. This is also an asymmetric harmonic oscillator, 1D harmonic oscillator. Okay. So for a 1D asymmetric harmonic oscillator, this is the state of a particle. So the question is to find out the average value of that particle. Okay. So here, first you have to check whether this wave function is normalized or not. Here this wave function is not normalized. Then how we can normalize? That is, normalization constant n is equal to 1 by root of 2 by root 3 whole square plus 1 by 3, that is root 3 whole square. That is, we get 1 by 4 by 3 plus 1 by 3, that is 1 by root of 5 by 3, that is root 3 by 5. That is, root 3 by 5 is the normalization constant. So the normalized wave function psi will be equal to n psi, right? That is equal to root 3 by 5 into 2 by root 3 psi 0 plus I by root 3 psi 1. That is, normalized wave function is equal to, we can cancel this root 3, that is 2 by root 5 psi 0 plus I by root 5 into psi 1. Now we have to find out the average energy. That is, we know the expression is summation S ES PS. Okay, so we have to find out the probabilities. That is, for this wave function, the square of coefficient is P0, that is 4 by 5, and the square of this coefficient is P1, that is 1 by 5. And we have to find out E0 and the E1. We know the expression for energy for a asymmetric harmonic oscillator, that is En is equal to n plus half h cross omega, where n can have values 1, 3, 5, etc. only. Okay, and this corresponds to ground state, this corresponds to first excited state, and this corresponds to second excited state. Okay, so E0 will be equal to the ground state, right? That is, n should be 1, that is 3 by 2 h cross omega, and the E1, that will be the first excited state, that is 3 plus half, that is 7 by 2 h cross omega. Now we can substitute all these values in this expression, that is, expectation value of E is equal to summation S ESPS is E0 P0 plus E1 P1, that is equal to 3 by 2 h cross omega into P0, that is 4 by 5, plus E1, that is 7 by 2 h cross omega into P1, that is 1 by 5. That is equal to 12 by 10 h cross omega plus 7 by 10 h cross omega, that is equal to 19 by 10 h cross omega. That will be the average value of energy. One more example problem. Find expectation value of E for the following wave function of a 1D symmetric linear harmonic oscillator. So the wave function is psi is equal to 1 by root 6 psi 0 plus 2 by root 6 psi 1 plus 1 by root 6 psi 2. First you have to check whether this is normalized or not. How we can check? Take the coefficient, that is coefficient are, these are the coefficient. Okay, so square this coefficient, add them, that is 4 by 6 plus 1 by 6. If you are getting 1, then it is a normalized. So here we get 1, therefore this is a normalized. Okay, so no need to do any normalization. But if it is not equal to 1, then you have to normalize, right? So what is the expression for expectation value of E? That is ES PS summation S ES PS, that is equal to, here there are 3 states, so we have to sum over 3 states, that is E0 P0 plus E1 P1 plus E2 P2. That is for asymmetric oscillator. We know the ground state energy is 3 by 2 H cross omega into P0. That is P0 is square of the coefficient psi 0, that is 1 by 6 plus E1, that is 7 by 2 H cross omega into P1. P1 is square of coefficient of psi 1 of a psi 1, that is 4 by 6 plus E2, that is second excited state of asymmetric linear harmonic oscillator, and that energy is 11 by 2 H cross omega into square of this coefficient of psi 2, that is 1 by 6. So just multiply and add and you will get the result. So this is a work for you.